Hey, this is Rich Venditti from the NC State paper-making pilot plant. Today we're going to look at a flow control loop. We're going to start off with a feed tank. So we've got a tank right here, industrial size. And then at the bottom of the tank, very difficult to see, we've got a pump. It's right underneath the tank. And then basically that pump actually pumps fluid up through this pipe. So this pipe right here, and then it goes through this pipe, then it goes to here. This is a flow meter. It's a magnetic flow meter. It measures the flow of the fluid going through the pipe. And then what we have right here is a control valve. That control valve, you can see the orange hose going in. That's compressed air, and that actually adjusts the valve position. And then actually we just have the water going straight back into the feed tank. Here's the pump that's pumping out of the bottom of the tank. That's that blue pump right there. It's a centrifugal pump, so it has an impeller in it that's spinning, provides kinetic energy to the fluid, and then that is converted into pressure, and the pressure pushes it up through the pipes. The green thing right there is the motor, and that motor actually turns the impeller in the pump. Here's the tank. Tank diameter is about 12 feet, and you can see the return liquid in our flow loop. We got an impeller in the tank, things stirred, and we like to keep the level of the tank at least a quarter to a third. The pump that we're using requires a certain hydrostatic pressure to push, or head that pushes the liquid into the pump, preventing something called cavitation. Just to give you an idea, that flow is through about a 4-inch pipe, and that's about 50 to 100 gallons per minute going through there. This is the control panel for the flow loop. What you'll see here is we've got our feed tank, and there's our pump. That pump is pumping up through this line. We've actually got a pressure transmitter that we don't use in the control. Well, here's our flow transmitter, and then the fluid follows up. We have a control valve, and then it just gets recycled back into the tank. This is our control window, and what you see is there's buttons to go in automatic and manual. Currently we're in manual control. The valve position is manually set. Right now it's at 48.8% open, and what that's doing is generating about 138 gallons per minute of flow through the loop. In manual control, we can adjust the control valve by ourselves manually. So for instance, I'll drop the control valve down to 25% or so, actually 21.7%, and what you'll see is that the flow decreases. If we increase the valve position, the flow will increase. Now, in manual control, the nice thing is that we set that control valve so we know exactly where it's going to be. However, we don't exactly know what the resulting flow will be. On our control panel, we have the blue line, which is actually the valve position, and the yellow line, which is the flow. And you can see when we decrease the valve position, the yellow line, the flow decreased, and then it increased again when we increased the valve position. What you'll notice is that there is a little bit of a delay between when we change the valve and when the flow starts to change. And you'll also see that the flow changes, and that change is actually a first order plus dead time dynamics. It does not change in a rapid step change. It changes in an exponential decay to a new steady state value. One of the powerful things about feedback control loops like this is in automatic control, now what's going to happen is we will actually set a set point for the flow rather than directly change the valve. We're going to change the set point, and then from the set point change, the computer is actually going to manipulate the valve to get to the new set point. So for instance, now we can take the white arrow right here from 145, and what we'll do is we'll drop that set point flow down, and we'll watch the computer control the valve and then the flow. So now what we did was we just changed the set point to 73.9, and what you'll see is that blue line, that's the flow, is actually decreasing. The blue line, that's the control valve, that's decreasing. And what that's doing is decreasing the yellow line, which is the actual flow. And the computer is trying to drive the actual flow towards the set point. So right now our valve is at about 25% open, actual flow 90, and our set point 73.9. So the computer should actually be decreasing the valve more until we get the actual flow to equal the set point. You can see now the actual flow is at 80, and the set point is at 73, and it continues to decrease. Here's a trend line. Blue is the valve, white is the set point, and yellow is the actual flow. And the beautiful thing about this is the computer's doing all the hard work to drive the actual flow, the yellow line, to the white line. And you can see at this point right now, we're basically at the actual flow equaling the set point. At this point, we would say we have no offset. Well, how does the computer actually drive the actual flow towards the set point? Well, there's a feedback control algorithm, and basically we have two parameters working right now, a gain and a reset. Basically the gain takes the error, which is the actual minus set point, and multiplies it by the gain, and uses that as a controller output to manipulate the valve. In addition, we have what's called a reset time. That's 10 seconds right now. And basically what that does is it integrates the error in the past and then multiplies that by the gain and divides it by the reset, and then that's called the integral action, and that will actually compensate when the gain does not remove all of the error that's in the system. Overall, this control loop, flow control loop, is pretty simple, but basically has all the integral components of a feedback control loop. Switching from manual to auto, changing the tuning parameters in the feedback control algorithm, and all kinds of industrial hardware that's used to control the system.